I understand time, but I don't think about it much. This quote by the philosopher Augustine of Hippo, who lived over 1500 years ago, remains relevant today. If we consider time travel, not the usual progression from childhood to old age, but actual travel to the future or past, that's what we truly desire. And that's what is incredibly difficult to imagine in practice. While the question of returning to the past remains controversial, science doesn't rule out the possibility of traveling to the future. Physics explains time as the fourth dimension. Simply put, everything in our reality has width, height, and length, 3 dimensions. The length in time is the fourth. The fact that we measure time in minutes, hours, or days doesn't mean it has a constant speed. This can be compared to a river's current. The water moves at different speeds in different places, just like our elusive time. It is precisely in this relativity that the key to traveling through the fourth dimension lies. Albert Einstein hypothesized that time can be slowed down by matter, and he was right. The heavier an object, the more time slows down near it. Proof of this is the GPS satellites orbiting above us. Each satellite has super precise clocks that run ahead by 1/3 of a billionth of a second every day. Of course, these clocks are recalibrated daily. This isn't due to malfunctioning clocks. It's because of the Earth's large mass, making time flow slightly slower on its surface than in orbit. Now imagine the most powerful natural time machine, weighing as much as several million of our suns, a black hole. Stephen Hawking calculated that if a spaceship with people were put into the correct orbit near a black hole at the center of our galaxy, time for those daredevils on board would slow down by half. If they were to travel along this orbit for 5 years, 10 years would pass on Earth. The crew would return to a future Earth where their former peers would be 5 years older. That's a journey through space and time. Another key to leaping into the future is your speed of movement. If you move at a speed close to the speed of light, you will inevitably be transported to the future. To understand how this works, Hawking devised a super-fast train whose passengers would find themselves in a real-time machine. Let's lay a track for this train around the Earth. The train would circle, gaining speed faster and faster. As we know, the laws of physics prevent it from reaching the speed of light, but it can approach it. So our train is already making 7 revolutions per second. Returning home after a week, the passengers would see that not 2 weeks, not even a month, but a whole 100 years have passed on Earth. In this situation, time slows down for the travelers significantly more than in the orbit of a black hole. Why does it slow down? It's a so-called protection of the permissible speed. If one of the passengers suddenly decides to run as fast as possible in the direction of the train's movement to exceed, or at least catch up to, the speed of light, they will be greatly disappointed. The laws of nature will always slow down time to protect the permissible speed. By the way, you all know an analog of such a train, the Large Hadron Collider. It's there that scientists discovered that time slows down for objects moving at 99% of the speed of light, and even in the zones of rapidly decaying particles, however fast they are, they exist for only 25 billionths of a second. But when accelerated to the speed we know, they exist 30 times longer. Here's another fact supporting the reality of events like time travel to the future. Travel to the past, as we've already said, is not yet even conceivable. The very thought of it creates many paradoxes related to the idea that in such a scenario, effects would precede causes, which seems impossible. However, if we adhere to the multiverse theory, you could travel to your past, but only in a parallel universe. Then your actions wouldn't affect you in your native universe, though you wouldn't be able to return. Almost everyone dreams of unraveling the mysteries associated with this and gaining control over time, which sometimes seems merciless. In 2014, based on the scientific works of the renowned physicist Kip Thorne, the stunning science fiction film Interstellar was made. In this film, the Nolan brothers attempted to show what the fifth dimension and time travel might look like. Did they succeed in realistically recreating, from a scientific point of view, something we have never seen? What do we know about the dimensions of our universe? Currently, the most stable theory in theoretical physics is M-theory, which in turn is an embodiment of string theory. M-theory suggests the existence of as many as 11 dimensions. In addition, there is F-theory, which postulates 12 dimensions, 2 of which are temporal. However, we can currently only perceive 4. Our familiar three-dimensional space, as it were, moves along a line and only in one direction. We call this line time, which serves as our fourth dimension, our lifeline, along which we can only move from past to future. For illustrative purposes, if we take a ball at rest, for a two-dimensional space it's a circle, for a one-dimensional space a line, for a three-dimensional space a sphere or the ball itself, and in four-dimensional space the same ball, but jumping throughout its journey, creating a figure resembling a tube with hemispherical ends. In four-dimensional space, the ball is a tube, and the sphere is a three-dimensional projection of this four-dimensional figure. But what would happen if we saw the fifth dimension? In Interstellar, they showed a version of the fifth dimension as conceived by the filmmakers, a kind of hypercube consisting of a huge number of rooms. Each of these rooms represented the three-dimensional space at any moment of its existence, and the hero communicated with his daughter in the past using gravitational anomalies. This representation does not contradict scientific interpretations. This dimension can be called a higher-order plane, consisting of a set of separate branches from the lifeline, that is, all possible events. And if the assumption about the existence of an infinite number of parallel realities is correct, then in the fifth dimension we should see all the lifelines of all possible parallel realities extending in an infinite number of directions. It's hard to imagine how this could be possible. Are there beings who already have access to the fifth dimension? What would their lives look like then? The laws of physics there would most likely work according to a different scenario. It is in the fifth dimension that four-dimensional space-time must bend to bring 2 points on a straight line closer together, causing the so-called curvature of the space-time continuum, without which time travel is unlikely. We can confidently say that for beings who have access to other dimensions, time means something else. Interstellar gave us a beautiful artistic visualization of what scientists are only writing about. Humanity has not yet been able to see or feel more than 4 dimensions and influence time. Therefore, we are very grateful to the creators of the film who were able to imagine and show us the fifth dimension and gravity through time, which truly shocks us because a person is not yet able to encounter something like this. What if that's how it really looks? Such a film makes people think, reason, and become interested in science, and that pleases us. Now tell us, where would you like to go traveling through the fourth dimension? Meanwhile, we've already been to the near future and learned that you'll like our video, so that our next episode will be even cooler. Therefore, we say a huge thank you to our best viewer. Don't forget that every like makes science more popular. The reality we observe daily is quite subjective, as each person interprets what they see in their own way. Unfortunately, only a tiny fraction of the universe is accessible to us for observation. Representatives of Homo sapiens resemble rabbits in a labyrinth. We can choose the direction of movement, but seeing the whole picture is not an option for such a tiny and helpless observer. Ancient stargazers were not wrongly equated with heavenly beings, for they understood the language of the heavens, able to decipher the whispers of distant stars. And even now, the profession of astronomer is respected, as these people are considered to survey the entire visible universe, and almost nothing is secret to them. But there are things in the world that fill even the most learned men with superstitious awe, let alone ordinary people. For example, at first glance, the question of how many universes our universe contains sounds strange. People are used to thinking that they live in a huge bubble filled with myriads of galaxies in which stars shine brilliantly and planets invariably revolve. All this is true, but there is another perspective on this topic. The path to realizing that we are not the center of the universe was difficult and thorny. The geocentric system, which assumed that the Earth was the foundation around which other celestial bodies revolved, has long since become a thing of the past. It was replaced by the heliocentric and then the galactocentric system. Modern humanity has realized that our metagalaxy lacks a center as such, and it holds many unsolved mysteries. Perhaps not one, but hundreds of millions of universes, enclosed in a common network, successfully coexist near us, but we are unable to see it, similar to a rabbit in a labyrinth. Philosophy, a science that wholeheartedly supports the theory of multiverses, with many representatives believing that all possible life scenarios will necessarily be embodied in one of billions of worlds, since possibility and reality are closely intertwined. Simply put, if you couldn't decide on a round-the-world trip in this universe, in another you will definitely become the second Magellan. In one world you are a king, in another a slave. If you are watching this video here and now, in another universe at this moment you are flying on an airplane, in a third you are sleeping. In some realities, the worst possible scenarios are realized, and in others, the best, and this does not contradict universal laws. Judge for yourselves. A coin cannot simultaneously fall heads and tails. The theme of variant realities has been creatively reinterpreted in many fairy tales and science fiction films. Baum's The Wonderful Wizard of Oz, Wells's The Door in the Wall, or the extravagant film Run Lola Run. Similar theories find confirmation in quantum physics. Hugh Everett, the famous American astrophysicist, in 1950 formulated the many-worlds interpretation, according to which our familiar world is actually a small part of an infinite number of universes. How did these strange realities arise? The generally known starting point of our universe's genesis was the Big Bang. What happened after that is undoubtedly unknown. Theories differ. One hypothesis states that due to the lightning-fast expansion in the first seconds after the Big Bang, the universe literally inflated, increasing in size by 10 to the millionth power. The resulting space, filled with false vacuum, generated many worlds, including ours, possessing different properties, physical constants, and conditions. If we could look into one of these universes, this world would probably seem very strange to us. Given the considerable size of the titanic bubble of the multiverse, the boundary of neighboring domains, spheres, is incredibly far from us. Perhaps the answer to the question of where the so-called brains and walls of neighboring universes are hidden lies in the mystery of dark matter, which makes up far more than the usual 5%. In the opinion of many scientists, these undiscovered worlds fill this very hidden mass. But the most interesting question is what the neighboring universes are like. It is human nature to measure the surrounding world by our own measure, so theories about neighboring universes are to some extent anthropomorphic. But most likely, in these multiple realities, the laws and conditions are completely alien to us. This thought incredibly teases the imagination, doesn't it? We just learned that these universes represent universes of our clones with different lifelines. But not only the American astrophysicist Everett reasoned on this topic. Andrei Linde, another adherent of this theory, believed that the universe is fractal, that is, you can even travel through them. True, such a tourist voyage would inevitably drag on for tens of millions of years. These mysterious worlds are compared by scientists to a huge container in which water is in different states of aggregation. In one part ice, in another gas, in a third ordinary H2O, or snow, and so on ad infinitum. But at the same time, all the worlds belong to one universe from which they branched off. These are not the only variations on the theme. There are even more unusual versions. Martin Rees, a professor of cosmology and astrophysics at the University of Cambridge, in the 1990s voiced the idea that nature creates multiverses for the purpose of experimentation as a field for research. Rees believed that multiple universes are absolutely empty, since a rather rigid set of conditions is required for the origin of life. A narrow temperature range, the presence of water, location in the habitable zone, the venerable age of the star, and other necessary points. These conditions are met in our world, but they are unlikely to be repeated in neighboring ones. Linde also believed that many universes are born dead, without a chance of development, and some collapse immediately after their appearance. Although it is possible that in other worlds, the cards fell out as favorably as in ours, so the conditions in them would be similar. The most controversial, but original, are the Max Tegmark universes of the professor from the University of Pennsylvania. The physicist believes that neighboring worlds are a rigid set of mathematical formulas and laws existing outside of time and space. This is the most terrible, inevitable variant, since algebraic canons make the world obligatory and unchanging. So, if we assume that numerical universes are full of suffering and evil, then it will last practically forever. A description of hell. There is another interesting point related to the multiverse that has repeatedly occurred to everyone interested in this topic. How to get into a neighboring universe? Does a proverbial portal or wormhole, sometimes called a black hole, exist? Andrei Linde argues that to find the boundary of worlds and cross it, two main conditions are necessary: longevity and a very large energy reserve. The first is because the distance to the nearest boundary may be 10 to the millionth power light years. The second condition is also indispensable due to the immeasurably high energy potential of such a membrane. But if a person nevertheless overcomes this impassable wall, most likely, instant death awaits them. The body will simply decompose into particles or radically change its properties, which will also be incompatible with life. The true nature of the universe. What is it? People have been trying to answer this question for hundreds of years, picking up various theories, inventing stories to describe that world as accurately as possible. But the more we delve into it, the more we understand that there are many oddities, and it is not easy to comprehend the true nature of such complexity. For example, string theory is so strange and controversial that many scientific minds from all over the world are trying to confirm or refute it, considering it a universal theory of everything. Why was it invented, and how truthful is it? Perhaps this is someone's next invention to understand the reality around us as much as possible. Scientists tried to examine things at the maximum proximity. Just imagine how amazing the molecular world might be. It would draw amazing pictures and landscapes. Molecular structures consist of tiny particles called atoms. A basic school physics course states that an atom is the smallest particle of the universe, the basis of all reality. But if we look deeper, colliding two atoms together with great force, scientists realize that there are even smaller elementary particles. And here a new question arises. What is meant by the concept of seeing? For a person to see, light is needed. More precisely, an electromagnetic wave. The wave passes through space, hits a surface, bounces off it, hits our eyes, which in turn recreate an image from the received information. In other words, without light, we cannot see anything. Remember how much you can see in a dark room. But according to this principle, we can see large things. But what about very, very small ones? Electromagnetic waves simply do not see them and cannot touch them. This problem could be solved if it were possible to reproduce smaller electromagnetic waves with greater intensity. But there's a catch. High-intensity electromagnetic waves will damage elementary particles, so it will be impossible to study them accurately. This fact, due to its importance, was named the Heisenberg uncertainty principle, the basis for all of quantum physics. So how can we now study these elementary particles, determine their size, nature, and so on? Actually, we don't know. In the 20th century, two theoretical bases appeared for formulating the laws of physics: Albert Einstein's general theory of relativity, a theory explaining the force of gravity and the structure of space and time, and quantum mechanics, which is a completely different formulation for describing physical phenomena using the principle of probability. By the late 1970s, these two structures were sufficient to explain most of the observed features of the universe, from elementary particles and atoms to the evolution of stars and the universe as a whole. String theory is a theoretical framework that attempts to solve these and many other questions. The starting point of string theory is the idea that the point-like particles of particle physics can also be modeled as one-dimensional objects called strings. String theory describes how strings propagate in space and interact with each other. In this version of string theory, there is only one type of string, which can look like a small loop or segment of an ordinary string, and it can vibrate differently. At scales exceeding the scale of a string, the string will look like an ordinary particle with its mass, charge, and other properties determined by the vibrational state of the string. Thus, all different elementary particles can be considered as vibrating strings. In string theory, one of the vibrational states of the string gives rise to the graviton, the quantum mechanical particle that carries the gravitational force. Thus, string theory is a theory of quantum gravity. One of the main events of the last few decades in string theory was the discovery of some dual mathematical transformations that identify one physical theory with another. Physicists studying string theory have discovered a number of these dualities between different versions of string theory, and this has led to the hypothesis that all consistent versions of string theory are included in a single structure known as M-theory. The study of string theory has also yielded a number of results on the nature of black holes and gravitational interactions. There are certain paradoxes that arise when trying to understand the quantum aspects of black holes. At the end of 1997, this line of work culminated in the discovery of the ADS/CFT correspondence, a theoretical result that connects string theory with other physical theories that are better understood theoretically. The ADS/CFT correspondence is important for the study of black holes and quantum gravity, and it has applications to other subjects, including nuclear and condensed matter physics. One of the problems of string theory is that the full theory does not have a satisfactory definition under all circumstances. Scattering amplitudes are most easily determined using perturbative methods, but it is generally unknown how to define string theory non-perturbatively. It is also unclear whether there is any principle by which string theory selects its vacuum state, the physical state that determines the properties of our universe. The starting point of string theory is the idea that the point-like particles of quantum field theory can also be modeled as one-dimensional objects called strings. The interaction of strings is more directly defined by generalizing perturbation theory at the level of Feynman diagrams. This means replacing a one-dimensional diagram representing the path of a point-like particle with a two-dimensional surface representing the motion of a string. Unlike quantum field theory, string theory does not have a complete non-perturbative definition, so many theoretical questions that physicists would like to answer remain out of reach. So, string theory is not a theory of everything, but like the history of the particle from point to string, it can be very useful. We still don't know exactly what the true nature of reality and the universe is, but we will continue to seek a solution to this question, trying to find out the truth, hoping that the truth will eventually be revealed to our minds. What do a spiral galaxy, a Dan Brown book, cephalopods, and prolific rabbits have in common? Nothing, you say? But the connection exists, and you will be convinced of this now. Let's start from afar. The great mathematician Leonardo Pisano, better known as Fibonacci, at the beginning of the 13th century, in his book, revealed an interesting observation based on the calculation of a hypothetical rabbit population. He took as a basis a sexually mature pair that, from the second month of close contact, began to actively produce offspring, not chaotically, but in an original sequence. Each month, the number of animals became equal to the sum of the 2 previous months. For example, the initial number is 1 pair of rabbits. In the next month, there are 2, and in the third, 3, then 5, 8, 13, and so on. Thus, the Fibonacci number sequence was born, stating that the sum of 2 preceding numbers is equal to the next number. 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, 3 plus 5 is equal to 8, and so on. This sequence can be continued indefinitely. Why do we need mathematical thickets? Impatient listeners will ask. The fact is that the Fibonacci numerical order is the basis, the starting point, guided by which nature creates new forms, starting the process literally from scratch. The ingenious Leonardo da Vinci, in essence, didn't discover America when describing ideal human proportions. He simply clothed in graphic form what his namesake spoke about when he discovered the Fibonacci sequence. Even before our era, this postulate was mentioned by the ancient Greek mathematicians Pythagoras and Euclid in his Elements. The Fibonacci numerical spiral is the law of world perfection. Its manifestations are found in science and art, in nature. Ideal proportions are calculated taking into account the ratio of the larger part to the smaller, as well as the whole segment to the larger. Adding to this the inversely proportional ratios between neighboring numbers, they fluctuate from 0.618 to 1.618. But there is a peculiarity. The further the sequence moves away from the starting point, the more the deviations are smoothed out, gradually bringing the numerical sequence closer to the so-called golden ratio, or the famous number phi, with infinitely continuing, never repeating decimal fractions. Connecting squares according to this sequence, you can see amazing metamorphoses. If you draw smooth lines through the corners of geometric figures, a spiral emanating from one point will open up to your gaze, the alpha and omega of the universe, the mysterious formula of nature that it uses when creating its masterpieces. Let's turn to the meaning and manifestations of the golden ratio in the natural world, where we can see true mathematical perfection. First of all, in the canonical proportions of the human body, as depicted by Leonardo da Vinci in his sketch of the Vitruvian Man. But this is a classic example. Others are literally everywhere. Underwater, in deep space, and sometimes literally fall on our heads. For example, an ordinary pine cone. Look closely at it. Its scales are arranged spirally, and the numbers of participants in neighboring spirals do not deviate at all from the Fibonacci sequence. And that's not all. Examples include ordinary sunflowers with their geometrically precisely arranged seeds, Romanesco broccoli, aloe vera, and the shells of some mollusks. If you look inside human DNA, there are 23 chromosomes in somatic cells. Carriers of hereditary diseases are 8, 13, and 21, an amazing spiral pattern. It is also visible in the fury of hurricanes, in the embryos of plants and animals, in the patterns of the arrangement of buds on a tree and leaves on a stem. It can be seen in the curls of the horns of ungulates, the intricacies of a spider web, and the proportions of the bodies of dragonflies and lizards. But not only living organisms obey this magical formula. Man-made structures also strive for perfection. If you draw a Fibonacci square on a large sheet of paper and then erase all the lines inside, you get a golden rectangle, a figure whose side lengths are in ideal proportions, with a coefficient of the ratio between the numbers equal to an infinite decimal fraction, or the number phi. The phenomenon is also that if you separate squares from the inner rectangle of this structure, you will still get a rectangle, only smaller, and so you can continue indefinitely. Designers successfully use the golden ratio rule to give their projects proportionality and harmony. It turns out that beauty has an impeccable mathematical measure that determines visual perception. Architects and artists of antiquity also did not disdain this rule. For example, the Athenian Parthenon, the Mayan pyramids, Notre Dame de Paris, Da Vinci's The Last Supper, the statue of Athena, the great Zeus, the Belvedere Apollo, and the inimitable Nefertiti ideally fit into the golden rectangle. Moreover, according to the Fibonacci sequence and the laws of the golden ratio, you can calculate the optimal sound volume, comfortable temperature, humidity, and pressure indicators. These mathematical rules also operate in literature and music. The harmony of the works of Pushkin, Lermontov, Beethoven, and Chopin is based on the Fibonacci number sequence. If we abstract ourselves from earthly problems and turn our gaze to the heavens, it becomes obvious that the solar system obeys the same universal cosmic code. It has been calculated that the distance between the Sun and Mercury, added to the kilometers separating the incandescent planet and the cloudy Venus, exactly corresponds to the gap between Venus and the Earth. The solar system, the galaxy, this is the Fibonacci spiral, the center of which is a star or a galaxy. Who is this mysterious architect who programmed the numerical sequences, as in Dan Brown's famous book, The Da Vinci Code? And did everything go as he planned? It turns out that the Fibonacci spiral and the golden ratio are laws uniting the micro and macro worlds. A comprehensive blueprint with precise calculations that allow us to create incredible structures, works of art, and comprehend the mysteries of the universe. Essentially, the key to the structure of existence. Perhaps this sounds somewhat pompous, but think what would happen to the everyday picture of the world and to us if this universal pattern did not exist. Perhaps instead of strong and harmonious human bodies, the Earth would be inhabited by unimaginable freaks wandering unconsciously among the vegetative chaos. And would the planet and the universe as a whole exist at all? Having answered one question, another appears, and then two more, 3, 5, 8, 13. Do you get the hint? Tell your friends about these amazing, albeit seemingly familiar things by sharing this video with them. Participate in the discussion of interesting topics in the comments. Don't be afraid to object and argue. This, as is known, helps the truth to be born. Is there life on Mars? Science doesn't know yet. These words, spoken several decades ago, remain relevant to this day. Moreover, the question of the habitability of the red planet has frankly tired many, but let's try once again to carefully peer into the rusty surface of our neighbor and reflect on this. If life on Mars existed, what would it be like? When talking about Mars, dried-up riverbeds are often mentioned, through which rivers once flowed, meaning that life probably thrived. Where did it go? Did it go underground? Did it become the cause of the appearance of mankind? Or did something catastrophic happen? As one of the apocalyptic scenarios, scientists propose a scenario with 3 satellites. Now, Deimos and Phobos orbit Mars. The latter is closely approaching the Roche limit and will soon be torn apart by the planet's gravity. The consequences of the fall of fragments of this huge potato will be terrible. Volcanoes will awaken, the atmospheric haze will disappear, and the planet's surface will become incandescent. Perhaps this has already happened after the fall of Thanatos, the 3rd satellite of Mars, which we were not destined to see. But let's move from hypotheses to facts. Official data indicate that none of the probes, Mariner, Mars, Viking, Phoenix, found any life forms in samples of Martian soil, nor in numerous shots of the celestial body. But in 2012, a landmark experiment was conducted confirming the theory of Mars as a planet of past life. Scientists collected samples of algae and lichens growing in the Antarctic and placed them in an artificial environment, simulating the Martian atmosphere. In a month, the plants not only did not die, but also grew significantly. This means that there is definitely a chance of survival for at least some microorganisms on the red planet. Research continues, missions are planned, so a definite answer in this matter will not be given soon. For example, in June 2018, the Curiosity rover found a number of organic molecule compounds in Gale Crater on Mars. The results of the interplanetary station's work on July 25th of this year are even more surprising. A large underground lake has been discovered on Mars, located near the planet's south pole. This is the first case of finding such large reserves of liquid water. It is quite possible that the bacteria that died out on land, due to some circumstances, continue to survive in this strange lake. The reservoir, 19 kilometers wide, is very salty and most likely resembles the famous subglacial Antarctic Lake Vostok. But this is only an outward resemblance. The water in it is unusually cold, down to -30 degrees, but does not freeze due to the high concentration of salt. But for bacteria, this is hardly good news. The lake is saturated with perchlorates, which are poisonous to almost all known life forms. Almost, but not all. On Earth, there is a bacterium, Dichloromonas aromatica, that can break down potassium, magnesium, and sodium salts into more digestible compounds, chlorine and oxygen. They breathe the latter and thus survive in a seemingly completely unsuitable environment. So why shouldn't similar organisms exist in the Martian lake? On Earth, there are examples of creatures that amaze with their ability to survive. For example, in mosses and lichens, there is a microorganism called a tardigrade or water bear. The Martian lake would not be cold enough for it, since the temperature range of the tardigrade's survivability is from -200 degrees Celsius to +150 degrees Celsius. By the way, the presence of organic life on Mars is also confirmed by seasonal methane bursts. This gas can be produced by colonies of methanogens, which, by the way, reproduce very quickly. The number of some species can double every hour. Therefore, it is quite possible that life on Mars is thriving, only it does not reveal itself to earthly observers. But bacteria are interesting to astrobiologists. Ordinary people want intelligent octopuses or little green men with sad eyes. Hence the question, what about complex life forms on the red planet? Let's allow ourselves to offer the viewer an allusion to the film Life, since its scenario presents this problem in an original light. Perhaps you shouldn't look for large creatures. Pay attention to bacteria. Let's assume that in each microorganism on the red planet, wherever it is and whatever it looks like, there is a capacity for lightning-fast growth and a resource of incredible survivability. What would happen if this ball of DNA, representing just one cell, due to an external push, comes out of a long-term anabiosis? Should Earth researchers consider it a friendly life form? In this case, the appearance of the creature doesn't matter. Something else is important: frightening survivability. Due to this circumstance, an alien organism growing at breakneck speed is unlikely to care about other life forms. Its own survival will be paramount, even to the detriment of others. Let's strengthen the equation with two unknowns by adding a third: a cold mind and a high learning index. As a result, we get a creature that, from harmless cells, in the shortest possible time, turns into a monster that carries the threat of death and destruction. That's how the situation was presented in the aforementioned film. So, having discovered even a hint of the presence of life on Mars, researchers should not rush to joyfully announce this to the Earth community and send samples to their home planet. On the contrary, as soon as possible, the unknown microorganism should be quarantined and closely observed. The conclusion suggests itself, which should not be forgotten by researchers and colonizers of Mars. A seemingly harmless and helpless creature can pose a great danger and even provoke a global catastrophe. This situation can be remotely compared to the action of invisible killers, viruses, which have claimed more lives than all the warriors on Earth combined. And if they acquired intelligence and grew significantly, then probably there would be no place for all life forms on Earth. One dominant species would have to be chosen. In any case, humanity needs to seriously consider whether it needs to try to find life on Mars. Hubble wishes its viewers only pleasant discoveries. Stay tuned for updates. The age of the planet we live on is estimated at 4.5 billion years. People have explored every inch of its surface, meticulously cataloged living organisms and plants, reached the unfriendly cosmos and the dark ocean depths. But there are places where hardly a single living person will ever be: the bowels of the Earth. In school, children are shown a schematic image on which our planet is presented in a cross-section and looks like an exotic giant cake. But what the Earth's interior actually looks like, no one has ever seen with their own eyes. The center of the planet is located 6,000 kilometers under our feet, and the deepest well drilled by humans, the Kola well, stretches for a laughable 12 kilometers. Each time the drill tried to penetrate deeper than permitted, the bowels immediately protested. Either they showered the daredevils with molten sulfur, or they enveloped them in poisonous gas fumes, or they completely destroyed the installation. You might ask how the scheme of the internal structure of our alma mater was formed. The answer is elementary, like much that cannot be measured with a ruler or weighed. Scientists have figured this out using indirect methods. For example, earthquakes and underground explosions seriously help in studying the structure of the Earth. Don't be surprised. This may be the only benefit these destructive events bring. So, we know that the Earth's womb, or core, is 3,000 kilometers away. Where did this information come from? When tremors occur, the planet becomes like a giant drum weighing 5.9 sextillion tons. Impulses acting on one side of the celestial body after some time respond from the other. The route of oscillations passes through various sections of the Earth's structures, and this determines what sound is obtained at the output. Two types of waves have been discovered: P waves and S waves. The latter are unable to pass through liquid, and at a depth of 3,000 kilometers they disappear without a trace. From this, scientists concluded that this is where the molten outer core lies. But geologists were in for a surprise. P waves during earthquakes or nuclear explosions behave differently. They don't sink in liquid but emerge from the opposite side of the planet, reflecting from the core at different angles. The conclusion followed. In the center of the Earth, in addition to the liquid outer core, there is a solid inner core. Its composition and other nuances of the planet's structure are not precisely known. The information is based on guesses, laboratory studies, and indirect conclusions. But we will still try to take a tour to where, according to the beliefs of many peoples, the river Styx flows and where some scientists believe ancient civilizations have gone, thousands of kilometers below where we usually bury our dead. In short, welcome to the Earth's center. Without special equipment and a suit, this event is impossible in principle. One should clearly understand the conditions that await someone who dares to undertake such a crazy journey. Incredible pressure, 1,000,000 times greater than the surface pressure. Hellish heat. The core's temperature is approximately the same as in the outer layers of the sun, 5,000 degrees Celsius. But our traveler is not timid. They are dressed in a nanosuit that literally does not burn in fire. Stock up on patience and courage. The first stage is the lithosphere, the solid shell of the Earth, formerly called Sial, from the names of the two elements that make up its composition, silicon and aluminum. It includes the Earth's crust and the upper layer of the mantle. The traveler will overcome the lithosphere relatively quickly, especially if they fall into the ocean, because under it the crust's thickness is only 5 to 10 kilometers, versus 50 under the continents. About 60 seconds of free fall will pass, and the fearless tourist will plunge into the magmatic layers, the kitchen of the Earth's interior, the constantly smoldering and boiling mantle. This is the gray cardinal of tectonic processes. It controls earthquakes and volcanic eruptions. But this is only the entrance to its kingdom. To overcome the first 60 kilometers of molten rocks, the tourist will need another minute, and then the most interesting begins. The asthenosphere and mesosphere. Hello, Tartarus. It is here that the traveler should look for devils with their proverbial cauldrons. This is the heart of the mantle. The temperature rises to 1,500 degrees. The depth of the layer starts from 100 and continues up to 2,800 kilometers. But in freefall mode, you will overcome this fiery layer in about half an hour. This is the thickest section of the Earth's structure, making up about 80% of the planet's mass. The tourist will not have it easy here. The guest will be met by pressure of about 140 gigapascals, coupled with hellish temperature, turning iron and magnesium into a very dense and simultaneously plastic material. Closer to the center, starting from a depth of 3,000 kilometers, the upper boundary of the outer core will open up to view. An unimaginably hot plus 4,400 degrees and a dark ocean consisting of molten iron and nickel. You will have to swim through it into the depths for almost 2,300 kilometers, ignoring electrical discharges and magnetic anomalies. In this boiling soup, the geodynamo process, forming the planet's magnetic field, is born. After several tens of minutes, the traveler will reach the Holy of Holies, the center of the Earth. The inner core, compressed by monstrous pressure,